to tell whether this particular person is having a disease. That's called quantitative results. So, in qualitative disorders, there are two methods. One is a method called concordance. Concordance means in a given family, two related individuals have the same disease. That is called concordance. If two individuals who are related in a given family is having a disease, that means that is concordance. But if they are not, that is discordance. So when one member is affected and the other is not, that is called discordance. And this particular concordance and discordance will measure the familial aggregation of the disease. And the familial aggregation of the disease is considered as a lambda. That is a familial aggregation. That is a symbol given to that. If you take a look at these disorders here listed on the left side, schizophrenia, Crohn's disease, a wide variety of multifactorial disorders. And if you see the siblings or the ones in which the disease has been found, some of them have very high numbers. Some are 12, 157. What does this mean? This means autism is having more familial aggregation. That is, it is more prevalent, much more prevalent in a given family. But the lambda can be derived by a simple equation. Prevalence of the disease and relatives of an affected person divided by prevalence of the disease and overall population. That is what the lambda measures. So that means if the population is having, let us say, about 5 out of 1,000, whereas in a given family, it is also going to be, let us say, 5 out of 15 you study. It is pretty high number. And therefore, that is telling you that that particular disorder has got a tremendous amount of familial aggregation, and therefore is going to be much more genetic component there. But if lambda is equal to only 1 instead of 150 or 7 or 8 or whatever, there is no familial aggregation. That's what it means. Okay? That means whatever in the general population, whatever frequency is there, same frequency is there in your family. So who cares? That's not really a familial aggregation. That's what it means. Therefore, by measuring familial aggregation, you can tell that that particular multifactorial disorder is having a genetic component, and also it is going to be focused, obviously it is being inherited in a multifactorial way in a given family. There is also one more approach to really measure multifactorial disorders as well. That's called case control studies. That is, you take the cases of those who have disorders and controls who do not have disorders, and then you measure the prevalence of the disease. So, obviously, the genetic contribution must be assessed in this. That's the reason why we are all studying all the familial aggregation as well as case control studies to determine how much of genetic components are playing a role and how much is environmental, how much is genetic. So, to assess the genetic contribution, you need to study extended families, and frequency of the disease must be monitored. If you have a positive family history compared to control, that is, the case reports are there, much more positive than that, then you can tell that there is a genetic contribution to these multifactorial disorders. But some people use spouses as controls. It doesn't make sense because lots of errors, because it's a bias is there. The spouse may not even want to tell that there is a disease in the family. So you cannot use those. And also there are other biases like recall bias it is called. Okay? That is, a proband's relative may be more informed than control relative because he knows about the disease in the family. So that's called a recall bias. So you have to be careful whom you take as controls. Otherwise, you're going to get misleading figures. Okay? So determining the relative contributions to the genes and environment to complex diseases is very important. One of the things we talked about is the concordance and allele sharing with relatives. And in order to tease out these environment effects from genetic components, what you do is you can go to these familial aggregation studies, but you can also go for the twin studies. The best studies are the twin studies. Familial aggregation is fine. But, for example, if you have monozygotic and dizygotic twins, so how does these alleles behave? Let us take a look at, first of all, let us draw a checkerboard. Let us say there are 4 alleles here, A1, A2, A3, A4. And this is the these are SIB1 and SIB2. That's the genotype of SIB1. That's all possibilities are written here, all alleles. And all allele possibilities are here. Now, if you take a look at the top one and the left one, A1, A3, etc. Both alleles are common here. So you just find out how many common alleles are there in SIB1 and SIB2. These are all 2 common. In this case, A2, A4 versus A1, A3, there is no common allele at all. That is completely different. Those 2 are different, these 2 are different alleles. So that's a 0. So if you take a look at other ones, like A1, A4 versus A1, A3, the only common thing between these is A1, there is only one allele is common. So if you take this checkerboard, what you are getting is almost the same figure will come. 0.25, that is 2 alleles common is about 25%. 1 allele common is about 50%, and 0 allele is common, no common allele at all is 20%. So that will add, at any given locus, shift share, that kind of, that's equal to only 1 allele. Okay? That's what a checkerboard is telling. But this allele sharing is absolutely greater in monozygotic twins.
Wouldn't it be 100%?
Huh?
Wouldn't it be like 100?
In monozygotic twins? No, it will be close to 50. Okay? So in a monozygotic twins, proportion of alleles common with the proband is 1. That's your question. Okay. So that is 1-to-1 correspondence. Okay. Whereas if you take a first degree relative, it is half. Second degree relative, 1/4. And third degree, 1/8. So those are the alleles which will be common within the SIBs. That is the number of alleles which will be common. So that is what will happen. The degree of relationship will definitely point out towards that. Okay. So if you take a look at the unrelated family member controls, adoptees and spouses, this figure will be messed up. Okay. But if you take a look at the multiple sclerosis, okay, the lambda is approximately 20 in the first degree relative, and it is 1 in unrelated. That tells that the familial aggregation is more genetic than environmental. Okay? So that's how they tease out what is contributing to environmental and genetic. So in twin studies, the concordance, if the concordance is less than 100%, so it has to be 100%, right? It's 1. But if it is less than 100%, let us say it is not one allele sharing as we talked about, that tells you that there are environmental factors. Anything less than 100% is environmental factors. Okay? So if it is 90%, obviously 90% is genetic, but 10% is environmental. Do you get that? So in general, all monozygotic twins will have a greater concordance than dizygotic twins. So if you study both kinds, it is easier for you to point out whether it is more genetic or more environmental. Here is a table which studies the number of disorders. And if you take a look at here, let us say 46, there is more in monozygotic twins, obviously there will be less. So always these figures will be definitely less than these figures. Because these are monozygotic twins. These are dizygotic twins. But look at this. Almost all of them, except this particular one is pretty high. This is next higher and next higher. So those 3 disorders, 70, 62, and 72, are the ones which are more genetic component compared to, let us say, 22. Okay. That means this, whatever systemic lupus erythematosus has got more environmental factors than genetic factors. So by looking at the concordance values in the monozygotic twins, it should be 100% ideally. Anything less than 100% is going to be more environmental. So that is telling you, if it is more value, that means it is more genetic factors. If it is slightly lesser value, it will be more environmental factors. Okay? So by looking at these values, you can tell whether it is going to be more genetic or more environmental. But there are a variety of limitations in twin studies as well. I don't want to go into the details of these. But for example, you can have somatic rearrangements in immunoglobulin genes in monozygotic twins, axin activation possibilities. All these things will come as exceptions, okay? Because they will not apply to genetic rules. These are all qualitative traits we talked about. In a quantitative trait, you need to look at the normal distribution of whatever assay you are using. And I'm sure you went through the statistics here, right? You know a little bit of statistics, or you didn't study, forgot. So you have normal distribution. Normal distribution means it is a Gaussian distribution. It's a bell-shaped curve with a normal distribution. There are sometimes it can be right skewed or left skewed and things of that kind. So I'm sure you remember the formula, which is S square is square root of y minus y bar over x minus 1, right? That's the formula that you use for finding the standard deviation. So S square will be the value that I told you, but then you go to square root of that, you will get a standard deviation. What it means, standard deviation conceptually means, if there is a population here, that is the mean of the entire value. Let us say we are talking about here, what is he talking about? He's talking about the stature, like inches tall, I think, and number of men studied on this side. So you got the mean is approximately 68 inches or whatever. That's the mean. So in a given population, if you take this is approximately 1 standard deviation, and this is 2 standard deviations below the mean. That is 2 standard deviations above the mean. So up to 2 standard deviations, that is all within the normal range. Anything beyond 2 standard deviation, that is going to depart from the normal range. So let us say that you are taking blood glucose levels. What is now, unfortunately, the American Diabetic Association keeps on changing the values every year. Okay. So when I studied, 120 is the normal, but now 120 is not the normal value. Now they reduced it to 100. Okay. So let us say 120 is the normal value of the blood glucose. There is a range. It could range from 100 to 130. You still were within the range. Okay. So, but let us say 120 plus or minus 10. Plus or minus 10 means 10 this side and 10 that side is a standard deviation. But if I go for 2 times standard deviation, that is 20, 120 plus 20 is 140, that is abnormal. That is hyperglycemia. Whereas 120 minus 20 will be 100, that is hypoglycemia, hypo. So on either side of the spectrum, you will have what is it called values which are beyond the standard deviation, and that is considered to be abnormal. So in a quantitative trait, you should always look for those values, not within these values. Okay, it's much more complex because the statistics is more. So in general, I'm sure that you studied these things, right? What is that rule you studied in a Gaussian distribution? Did you not study introduction to statistics in undergrad? I can't believe this.
You have to take calculus.
Take calculus. Okay, I don't want to teach you statistics here, but I can tell you briefly what I remember. In a Gaussian distribution, if you draw here, there is 1 standard deviation. This is 0. That is 1 standard deviation. And that is 1 standard deviation. And that is 2. That is 3. 2 and 3. There is a rule established by one fellow that this area will constitute 68%. 68, and if I draw a line between here, 68, that is 95. And then this 3 standard deviation will be 99.7, right? So those are the 3 values in a statistic.